This code sets up a simple deep learning model for automated stock trading using Keras. It loads essential packages like pandas and NumPy for handling data, datetime for managing times, and matplotlib for plotting charts. It also brings in financial data using the pandas data reader. For the neural network, it gets key components from Keras, including models and layers, and connects with scikit-learn for model fitting. The min-max scaler from scikit-learn is used to normalize the data before it goes into the neural network. The code prepares everything needed to create and run the trading algorithm. This code sets up start and end dates, January 1st, 1973 to March 31st, 2011, for a time range. It helps a trading algorithm learn from past data so it can make better predictions within these dates. This code is part of a trading system that uses the Keras machine learning library. It first gets stock data from Yahoo Finance using Pandas data reader for the GSPC symbol between certain dates, and saves this data in a variable df using the Pandas format. Then it removes the addJClose column because it's not needed for this strategy. Finally, it prints the last bit of the stock data to show the code worked. The code fetches, cleans up, and summarizes stock information. The code extracts the start and end dates and generates a list of the earliest dates for each month called first days. It does this for each month from the starting year up to the last year, only including months up to the end date. This list helps break down the data into monthly periods for analysis and forecasting. This code snippet is for setting up data for algorithmic trading with Keras. It starts by converting daily data into monthly averages. The code then excludes the last incomplete month to maintain accuracy. It constructs columns for the first days of the current and next month, and then for those days' opening prices. A growth rate column is created by dividing the next month's open by the current month's open. It calculates 12-month and 24-month moving averages to help predict the next month's prices. The code removes the first 2 years to clear out the empty moving average data and any remaining missing data to clean up the dataset before it's used for trading predictions. The code calculates monthly moving averages for a dataset using a monthly df function. It then displays the first and last 5 rows of the new data frame. The code also shows the moving average for March 1980 and the average opening values from March 1979 to February 1980. The moving averages cover 12 and 24 months before the current month. This technique helps identify long-term trends for algorithmic trading. This script is for algorithmic trading using Keras. It processes data to find the gross yield of a trading strategy. It adjusts a quote column in the data with a variable v, subtracts 1, and multiplies it with other columns to get a value prod. Then it figures out the number of years n years by dividing the length of v by 12. Gross yield is the prod minus 1 times 100. It also calculates the annualized yield by taking prod to the 1 vet n years power, subtracting 1, and multiplying by 100. The code helps assess a trading strategy's effectiveness over time. The code sets the tax CG variable to 0.26 and COM-BK to 0.001. These are used for tax and commission fees in the trading code. Setting them like this helps the code calculate costs automatically and lets you change the fees easily when needed. This code processes an array U by adding a 0 at its start and end to form a new array. It then identifies the positions where consecutive elements change. These positions are stored in 2 arrays, V and W. If there are no changes, i.e. V is empty, the code returns an array of zeros the same length as U. If changes exist, it creates another zero-filled array, setting some elements to 1 or minus 1 based on V and W, then sums up these values cumulatively. Finally, it reshapes the summed array to match the dimensions of V by U and returns this reshaped array along with the length of V. The code creates a NumPy array named U with 9 zeros and 1 S that symbolize binary signals for algorithmic trading. It goes through the array, adding 1S to a up list indicating an upward stock trend and zeros to a down list for a downward trend. Afterward, it counts the items in each list to gauge the trend's strength, which aids trading decisions. This function sorts numbers, separating the number 1 from others in a list. It makes a new list for the ones, adds them to it when found, and then combines this list with the original. This can help with certain calculations in binary trading, where ones need to be dealt with separately. This code is for automated stock trading with Keras. It starts by receiving a table of data and a list of numbers. The list size is divided by 12 to figure out how many years we're dealing with. A special function groups these numbers into 2 categories, W and N. Then it calculates a value A by multiplying a specific column in the data table by W and then adjusting it by the factor 1W using the num tool. Next, the code forms a new list that marks with a 1 where A is more than 1 and 0 otherwise. It uses this list to generate 2 additional lists by adjusting A based on whether its elements are greater or less than 1. It calculates a final list, considering taxes and fees, by a combination of these previous calculations. To finish, the code multiplies all the numbers in the final list and adjusts for the trading commission to find out the increase in value over the entire period. Then it computes 2 results: the average yearly growth rate and the total growth over the entire period considered. This code generates a smaller version of a dataset with a specified window size by successively shifting and adding portions of the data. The process forms a sequence of datasets that can be helpful for analyzing time series or training machine learning models like neural networks. It removes any incomplete rows and outputs the processed dataset with the window applied. The data-to-model function takes a data frame DFM and prepares it for machine learning. It first scales the data using min-max scaler, setting values between 0 and 1. Then, it creates a new data frame DG with specific columns from DFM, scaling these columns. Next, it selects columns for the variable x and divides the data into smaller sections using the createWindow function with a specified window size. After that, it reshapes x into a 3D array for the model. The function ends by returning x, which has the reshaped data, and y, which has the target output for each section. The code creates a window of 5 to select data sequences for training a model. It then uses data-to-model to organize the dataset DFM into input sequences x and the next data point y. Finally, it displays the dimensions of x and y to verify they are correctly formatted for training. This code divides a dataset called x into 2 parts, a training set and a testing set for use in Keras-based algorithmic trading. X is a 3D array with 72 entries. The first command fixes the size of the testing set at 72. The second command creates the training set, xtrain, with all entries of x except the last one. The third command creates the testing set, xtest, starting from the 72nd entry. The fourth and fifth commands do the same for the target array y, which is 1D. Splitting the data this way helps check how well a model works on new unseen data. This code sets up a simple LSTM model for automated trading. It begins with setting a window and features for the LSTM input. A sequential model is built in Keras, starting with a 300-node LSTM layer that outputs the entire sequence, followed by a dropout layer to avoid overfitting. A second 200-node LSTM layer outputs only the final result, with another dropout layer afterward. 2 dense layers with 101 node each use ReLU activation and uniform weight initialization. The model uses mean squared error for loss and atom optimizer with a 0.001 learning rate. It's designed to predict future stock market trends. This code uses the Keras library to create a simplified neural network model for algorithmic trading. The network is made up of several layers with distinct roles. It starts with a convolutional layer that processes the input data and then moves through ReLU activation. Another convolutional layer follows, with similar settings. Following this is an LSTM layer with 300 neurons meant to handle time series data, then a dropout layer to reduce overfitting. Another LSTM layer with 200 neurons comes next, offering only the final output, followed by another dropout layer. 2 dense layers are next, one with 100 neurons and another with just 1, both using ReLU activation. The model is finalized with a mean-squared error loss function and the atom optimizer, and it's then ready to be used. The code sets up a simplified LSTM model and stores it in model LSTM. It has an input size of window +1 and 8 outputs. After creating the model, it displays a summary that outlines its layers and sizes, helping us check if it fits our needs. This code sets up a function to lower the learning rate if the model doesn't get better after 25 tries epochs. It's for training neural networks with Keras. The function tells you what's happening during training, how much to cut the learning rate, and the lowest it can go. This helps the model keep learning and avoid getting trapped at poor solutions, making the training better. This code uses Keras to train an LSTM model aimed at algorithmic trading. It runs through the training dataset 400 times in groups of 24 data points at a time, without shuffling the data before each round. It adjusts the learning rate as needed for better results and tracks progress with a visible bar. The model's success is tested using a separate set of validation data. The code creates a graph with matplotlib to show how the model's loss changes throughout its training. It first fetches and plots the training and validation loss, then adds a title, axis labels, and a legend to the graph. Lastly, it displays the graph, helping to spot if the model is overfitting or underfitting. This code saves the trained LSTM model's weights in a file called lstm_weights.h5. By doing this, we can use the model again without retraining it, which is especially useful in algorithmic trading using Keras. It saves time and resources because we don't have to start over each time. The saved weights hold the knowledge the model gained from its training, allowing it to make good predictions on new data. This code sets up a simple trading neural network with Keras called Model Mix. It uses past data points window size and has 8 prediction units output units for future stock prices. The print command shows the model's details, like layers and parameters, to aid in adjusting and fixing it. This script trains a trading model with Keras. The model mix, learns from the training data xtrain, ytrain through the fit function. It will run through the data 400 times epochs in small groups batch size. It also checks its accuracy with test data xtest, ytest, and can use special features callbacks like adjusting the learning rate. The data is mixed up after each run through shuffle to improve learning. After training, it provides results for analyzing the model's effectiveness. The code creates a line graph to show training and testing loss values for an algorithmic trading model using Keras. It pulls the loss data from history mix and plots them, labels the graph with model loss, and adds axis titles and a legend. The plt.show command then displays the finished graph, helping to assess the model's performance. This code line saves the learned settings of a machine learning model into a file called mixweights.h5. This lets you use the model again later without retraining it from the beginning, and makes it simple to move the model to another system for immediate use. This code uses a machine learning technique to predict future stock prices. It starts with an LSTM model, which is a specialized neural network good at understanding patterns over time to forecast prices. Then it uses a mixed model, combining various methods for a second prediction. Both models work with the training data, xtrain. It's part of a trading system that employs Keras, a tool for deep learning, to analyze past stock price trends for future forecasts. The aim is to assist traders in making better buy or sell decisions based on these machine learning predictions. This code generates a chart comparing real and forecasted opening stock prices for a training data set. Initially, it adjusts the chart size to be big 30 by 10 inches. It then draws lines for the actual prices and predictions from 2 models, LSTM and a combined model. A legend labels each line. The chart includes a grid for reference, a title actual versus predicted opening prices on training set with large text size 25, and then it displays the final visual. This code is from a trading bot that applies the Keras framework. It predicts prices with 2 models, LSTM and a mixed one, and saves the forecasts in ypred LSTM and ypred mix for later use in the bot's decisions. Both predictions are based on the xtest data. The code creates a trading strategy with Keras. It starts by finding the prediction errors using np.diff to calculate the changes between predicted and actual values. These errors are then adjusted to the same size as the predictions. The np.maximum function is applied to keep only the positive differences or zeros, avoiding negative values. This step is done for two prediction sets, ypred LSTM and ypred mix, resulting in two variables, VLSTM and VMix. These variables are used by the trading algorithm to pick profitable trades based on the forecasts. This code makes a 30 by 10 graph to compare real data with LSTM model predictions. It plots both LSTM and mixed model results together, adds a legend with large text, and includes grid lines. The title is set before the graph is shown. This helps to compare how well different models forecast stock prices. This code makes a smaller data frame test from DFM based on the number of rows specified by mtest. It then makes a NumPy array VBH with the same number of rows, all filled with 1. Another array VMA is made by comparing two columns, FDCM open and MVAV12 from test, showing if FDCM open is bigger than MVAVG12. This code calculates the total returns for a stock or asset portfolio. It begins with an empty list named portfolio. A for loop then goes over the data, computes the returns using the stock's weight, and adds them to the portfolio list up to a certain point I. After finishing, it gives back the complete list of returns. This is useful for automated trading to make fast investment decisions. This code generates a small chart 30 by 10 to compare the performance of 4 trading strategies, buy and hold, moving average, LSTM, and mix. It uses gross portfolio to plot and label each strategy, includes a legend and grid lines, and has a title stating it's a comparison of strategies. The chart is then displayed, likely to show how each strategy performs over time. The code sets a time frame for testing the trading strategy based on the dataset's start and end dates and its duration in years. It prepares an empty table to compare 4 strategies, buy and hold, moving average, LSTM, and a combined approach. For each strategy, the code computes overall and yearly gross and net profits using specific functions. It then shows these results in the table, outlining the performance of each method.